Hello and welcome. I'm Pravir, and today I'm going to present Enhancing Feynman's Quantum Computational Positioning to inject new possibility into the foundations of the computing industry. This is based on a paper by the same name submitted to IEEE IEMCON 2022. So over the next 20 minutes or so, I want to essentially make the case to move from a probabilistic quantum computer that's been positioned by Feynman to a light-based emergent quantum computer. So in this presentation, I'm going to revisit Feynman's position. And the reason I do this is because he's been instrumental in setting the quantum computational industry on its current track. I want to introduce a quantum computational model of light. Then based on this model of light, I want to enhance Feynman's position, and in particular, his approach to simulating time, space, probability, and his thoughts on the size of a quantum computer. I'll revisit based on the quantum computational model of light. I want to revisit key equations in quantum computation of Schrodinger, Heisenberg, Euler, essentially looking at them from a non-probabilistic basis, and then briefly suggest some light-based quantum computational devices and conclude and summarize this presentation. I start with a quote by Richard Feynman himself. "We are at the very beginning of time for the human race. It is not unreasonable that we grapple with problems, but there are tens of thousands of years in the future. Our responsibility is to do what we can, learn what we can, improve the solutions, and pass them on." And the reason why I bring this quote up is that I feel that the probabilistic quantum computer is a great first step in helping us to grapple with what the quantum realm is. But also, I feel that it's nothing else or other than a beginning, and there's a lot more that needs to be done. And that's why I suggest the model of light that essentially is the focus of this presentation. So when we revisit Feynman's position, then his essential position on quantum computation boils down to being able to simulate nature. But the question remains is, what's our interpretation of nature? Because depending on the interpretation, then the simulation could be facile or complex. And the way that essentially Feynman looks at nature is that it's based on his view of the Copenhagen interpretation of quantum mechanics, and essentially getting to the idea of we can never really know what's happening at the quantum level. All we can do is make measurements, and as a result of the measurements, then any quantum object will collapse into a state and into something that's measurable. And by definition, we would never be able to know what's really happening in nature, but all we'll do is come up with a bunch of measurements. And this is essentially also giving insight into his view of nature, of Feynman's view of nature, which is probabilistic and non-deterministic from that point of view. And so he comes up with this idea of creating an imitating computer that will do what nature is doing with the same probability. And that's the basis of the probabilistic quantum computer. Quoting him, C, that stands for the computer, C goes from some state to initial state to a final state with the same probability that N, or nature, goes from the corresponding initial state to the corresponding final state. And for him, that should be the objective of this probabilistic quantum computer that is going to be built. And then he goes on to say, you see, nature's unpredictable. How do you expect to predict it with the computer? You can't. It's unpredictable if it's probabilistic. But what you really do in a probabilistic system is repeat the experiment in nature a large number of times. And that essentially is the edifice of all the quantum computing efforts that are going on today, because it's all based on this statistical probabilistic approach of mimicking nature. And so nature is seen as something that is essentially probabilistic, and the way we understand it is through statistics by measuring a large number of times to get to what nature is trying to do. However, in face of that, I'd like to just point out that if nature were indeed random, then it would be impossible for the intricate and repeated structure we see manifest in matter and life to continue to sustain itself. Because if there was a new quantum impulse, then the very basis of matter and life itself should change. And so, in my point of view, probabilistic quantum computers will likely really never cut it. They'll never really tell us how to imitate nature. And for that, we need, even if we were to go the path of imitating nature, we would need a different kind of model and outlook. And so I introduce the quantum computational model of light. And essentially, in this model, we can think of different layers of light that are also can be thought of as different conceptual spaces. So we have 4 layers of light. And the native state of light is imagined to be a state where light travels infinitely fast, and it yields these properties of presence, power, knowledge, and harmony. And the way it does that is because if we consider any volume, and then we have a light source at the center, since it's infinitely fast, it will be immediately present everywhere at the same time. So there's this property of presence. If anything not of the nature of light were to arise, it would be overpowered by light, and therefore there's a property of power. Since light exists everywhere, it would record the appearance or disappearance of things, and so would have a knowledge of its entire space. And so the property of knowledge arises. And then since everything is implicitly connected in light, there would be harmony that would exist. Now, due to an act of quantization, which physically would occur when light projects itself at some slower speed, less than infinity, then these things that we're calling presence, power, knowledge, harmony would objectify or differentiate, and we would have 4 sets of presence, power, knowledge, harmony that would practically be infinite sets. And then due to a further projection of light going even slower, there would be a further differentiation. And we can imagine at that layer that there would be infinite number of elements that would be created that would be unique combinations of the elements in these 4 diverse sets, and that's captured by this line over here. And then due to another act of quantization, where light projects itself at speed c, we would then essentially emerge with material reality that's typified by space-time, energy, gravity. But the way that space, time, energy, gravity relates to these antecedent layers is the following. So we have in the antecedent layer infinite number of unique seeds. And as light is projected at c, we can think of these unique seeds as needing an arena in which to express themselves, and that is space. So space becomes granular. Then each seed would have something that it's trying to express, and the expression would vary as per different rates of maturity. And so that captures the idea of time. And as something that's subtle becomes more concrete, it's accompanied by different kind of energy. And so that's summarized by this thing that we're calling energy. And then seeds have relationship with seeds, and seed has relationship with seed, and therefore is the idea of gravity. And so we can see that from this point of view, space-time, energy, gravity is nothing other than a symmetrical face of presence, power, knowledge, harmony itself. Because if we think about space, then space is typified by a large number of archetypes, so it becomes a vehicle for knowledge. Time itself is something that in which whatever is in a seed will happen regardless of obstacles, and so it becomes a vehicle for power. Energy becomes a vehicle for presence because that which is subtle materializes, and gravity becomes a vehicle for harmony, in that there is always a relationship between seed and seed and seeds and seeds. So we see that this model has an implicit symmetry by which these 4 properties in light are expressing themselves in the material layer as space, time, energy, and gravity. So that's the essence of this quantum computational model of light. And now if we revisit Feynman's position and his essential focus on simulating space-time probability to begin with, let's see what he has to say about space. So he says that everything that were to happen in a small space-time volume would need to be analyzable by a relatively small number of operations by a quantum computer. So he's saying that we can use a computer to essentially imitate or simulate space-time, some volume in space-time. But if that were to happen, then we would need space to exist in minute and discrete elements, which of course is different than our understanding or preconceived understanding of space, where it's infinitesimally continuously connected. And so here, what we see is that his proposition of simulating space is in fact very consistent with this model of light, because here, as I said, we have granularity in space created by infinite number of seeds that need the arena of space to play in. So there's that same granularity, but in addition, we can think about everything that exists in space as being governed by meta functions, because all seeds themselves, as we see in this model of light, has a meta function behind it. So when we are simulating space, we need to think not only of granularity, but also of the meta function that's operative at certain points in space. When we think about simulating time, Feynman's position on this is that points in space will not only be influenced by other points of space at a particular time, but also perhaps by points of space at future time. And this is in contrast to the idea of simulating time that arises from this matrix of light, because we are saying that space and time is part of a complex adaptive system, and that's captured by this holographic fractal model. But in this model, time, along with space, energy, gravity, is all emergent, and time is relative. And time essentially is relative because there's a meta function presiding over a seed, which allows that seed to mature at its own pace, depending on the other forces that are active. So again, it gives different implications for how you want to simulate time, as opposed to this idea of just seeing how a point of space is influenced by other points of space in the current and future time. So there's a difference in simulating time. When we come to the idea of simulating probabilities, then essentially Feynman's position is that we're simulating probabilistic nature, which is what nature is. And if we have a computer that itself is probabilistic, then we can do this. So essentially in a probabilistic computer, the output is not going to be a unique function of input, as is the case in a digital computer. However, from this model of light, the idea of simulating probabilities is different, because what we're saying is that we're dealing with a fundamentally mysterious realm that separates the invisible from the visible. And we can't rely solely on the visible, which is what's happening in a probabilistic nature, or the probabilistic approach to try and imitate nature. There's dynamics that are causing what's happening visibly, and we need to understand those. And so we're diverging from this idea of simulating probabilities by simulating this model that exists of light. So again, a fundamental difference to enhance Feynman's position. And then when we think about the size of the quantum computer, Feynman's position is that essentially the size would directly correlate with the space-time volume trying to be understood. But when we think about this model of light, in fact, we'd see that there's a sublinear scaling that drives in. And we don't necessarily have to have larger computers to understand a larger volume of space-time, because any volume of space-time is emergent and is governed by a series of meta functions and dynamics that occur in other conceptual spaces. So there's therefore smaller computers that can be applied to larger application areas. Now, given this non-probabilistic approach to coming up with quantum computers, it's useful to consider Schrodinger's equation, Heisenberg's uncertainty principle, and Eulers identity from a non-probabilistic basis. And very briefly, if we consider the components of Schrodinger's equation, then the I here would give us insight. The imaginary complex number is essentially giving us insight into the interplay of two dimensions. So we have the physical dimension, and then we have the antecedent dimensions. And as we saw that in the antecedent dimensions, the speed of light is going higher, but I made the case in numerous other papers that there's a direct correlation between Planck's constant and the speed of light. So there's an inverse. Planck's constant is a lower bound. The speed of light is an upper bound of any space-time space that we're looking at. And essentially, what that implies is that if we are looking at a wave-particle duality, then a wave already is implying a faster than light speed. So there's the speed of light faster than c. And since there's an inverse proportionality, Planck's constant would be quote unquote smaller. And since it would be smaller, it wouldn't be able to approach the threshold value by which matter can form. And so it would express itself as a wave. And so this again makes sense from this point of view, because we find that Planck's constant becomes smaller. And then essentially the rate of change or the way that the wave function is changing cannot be differentiated or fragmented from this fundamental dynamics of I and h over 2 pi. And this gives us insight into finally how the wave itself is changing. And this Hamiltonian expressed by that expresses some system energy is essentially only complete when we consider this antecedent with the physical layer, the dynamics fully. And so the interpretation here is that Schrodinger's equation becomes an arbitration to take information from behind the quantum veil and essentially compute it into material existence. And so the quantum computer, from this point of view, becomes creative as opposed to solely constructive. And the object of quantum computation then is to create something new rather than to regurgitate program-based instruction. And this newness is going to be dictated by the infinite number of unique meta functions that exist, suggested by this model of light. Now, when we think about reinterpretation of Heisenberg's uncertainty principle, you'll recognize the form over here, where essentially we have Planck's constant that in this interpretation is suggesting a boundary between the layers that separate physical layer from the antecedent layers. And there's a quantum fluctuation that's happening. And of course, the standard interpretation is that if there's, due to this fluctuation, one can never really accurately measure pairs of quantum properties, momentum and position, for instance. One would be known, the other not. But the implication as light goes faster is that uncertainty becomes less and less, and it becomes completely certain as light travels infinitely fast, which means that the way to think about this quantum fluctuation is that it's a play of the unique seeds or meta functions that occur in the antecedent layers, and therefore also that the notion of position, momentum, or space-time quanta are emergent rather than absolute properties. So they're emerging because of the way that the light matrix is operating. So essentially, when we consider what are the takeaways for quantum computation, then this notion of emergence of fundamentals such as space-time and quanta means that quantum computation is fundamentally creative as opposed to a constructive act. And then importantly, also that there's this presiding meta function that will want to maintain its integrity, but the process by which it does that might be variable, and that variability is something that Heisenberg's uncertainty principle is measuring on the surface. Now, when we think about Eulers identity, this can also be seen as a process of materialization. So Eulers identity connects together 5 key concepts in mathematics. And we can give these meaning when we consider the light-based matrix. And essentially, we can see that in fact, Euler's identity is summarizing a process of materialization. And the way that this works is that if we consider, for instance, the initial state to be 0, so that's pointing to some absoluteness. And then there's a state of identity that's also revealed in that absoluteness. And then there's a state of differentiation that's considered by 2. And then you have initial stability and manifestation that are considered by 3 and 4. Then what we can see is that this series of quantizations, in fact, is pointing to a process of materialization by which 0 yields to 1, yields to 2, yields to 3, which yields to 4, which is manifestation. But then I, E, and pi are fundamental to this process of materialization. And we get a quick hint of this because we know that E, the differential of E is itself E. And so this gives us insight that E is pointing to something that we can call exponential experimentation. Pi, the value of pi is between 3 and 4, 3.1416 approximately. And so we get a sense that it's essentially relating 3 to 4, so stability to manifestation, which gives us insight that there's stability subject to dynamism. And so when we consider, then again, 0 yielding to 1, to 2, to 3, to 4, appropriately leveraging IE and pi, we see that this is nothing other than a process of materialization that's non-probabilistic from this point of view. Now, when we then ask ourselves, what would be the nature of a quantum computational device, there's several things to consider. So first of all, what we're saying is that there's organic light-based outputs, and it's not random probabilistic outputs that are emerging at the quantum level. And when we use this a process of induction, and I've written about the reverse extrapolation elsewhere, but essentially, when we think about reverse extrapolation and we look at the order that exists at the cellular level, then at the periodic table level, then at the quantum particle level, we can see that all of those can be organized again as symmetrical faces of light. So there's 4 properties that animate them. So the reverse extrapolation suggests that the quantum level itself also has the 4 dynamics based on them, but more appropriately, the process of induction from the light matrix itself suggests that there's fundamental activity existing in the minutiae of space that is different than just random probabilistic activity. And so there's a different, this innate activity must be read differently, and there's a different genre of computational devices required to read and respond to this activity. And that's really what is being suggested here, is that such a device would need to have a different sight of the dynamics of the minutiae of space. And this sight is being hinted at by the light matrix itself. Now, some technological breakthroughs that would occur in taking this light-based quantum computational approach in contrast to the probabilistic approach is that the size of a quantum computer can be radically larger. And why? Because it would be based on atoms. So we're saying that, whether it's atoms or whether it's molecular plans and cells, since these all occur as per unique functionality and in ordered fourfoldness, therefore there's quantum dynamics that are active in the atom or in the molecular plans themselves. And this means that an atom can be used to create a quantum computer as well. We know atoms to be completely stable at room temperature, and therefore a quantum computer can be radically larger. When we consider the generated quantum state lifetimes of such phenomena such as superposition, annealing, entanglement, and tunneling, then we also, now since they're based on stable atoms, again, it will far exceed the qubit lifetime. When we consider gates that are being built on photons and atoms, again, will be much more reliable and stable. And as I suggested, there's a unique mathematics that points to pre-existing entanglement and superposition that, again, is apparent from the light matrix. And so there's a less subjectivity to, in fact, there'll be no decoherence from this point of view, where the functional mathematics itself is making sure that the meta function maintains its integrity no matter how things may appear to be at the quantum level. And that's something that needs to be an anchor in the creation of quantum computer, because we're saying that it's not probabilistic. It's in fact determined by these meta functions. So it's a completely different approach. And then, whereas today's qubit computers are at best 95% accurate, that simply won't cut it in terms of computation. But we know that atoms and molecules that exist stably at room temperature do have 100% accuracy in operations, which again is very important to consider. So summarizing and concluding, today's quantum computing industry has diligently followed Richard Feynman's envisioning of probabilistic quantum computer. And this stems from Copenhagen interpretation of quantum mechanics. So in this view, I want to point out, re-emphasize that it's impossible to really know what's happening at the quantum level, since any possibility held by a quantum object will collapse into a measurable state when measured. So by definition, you can never tell what's happening at the quantum level. By contrast, when you consider a light-based quantum computational model, it is suggesting what happens at the quantum level. So there's a fundamental and very important divergence here. And also what is being suggested as happening is that there's an implicit fourfoldness in light that continues to express itself in infinite low-ordered ways. So that's completely different implications for quantum computation. The model provides a means to understand and see nature differently beyond the facile approach that is confined to statistics and probability only. So Feynman's approach of simulating space-time and probability by a probabilistic quantum computer gets enhanced by thinking of space and time differently, as I've gone over in this presentation, because these are all emergent properties held by precise metafunction logic. So a different genre of quantum computers can emerge as a result. And then insight into this genre of quantum computers is further reinforced by non-probabilistically reinterpreting foundational equations such as Schrodinger's wave equation, Heisenberg's uncertainty principle, and Eulers identity, as I've done. And this new genre of quantum computers is going to be creative as opposed to constructive. And it's essentially, the important point is that this quantum realm that separates invisible from the visible must be endowed with mysteries that far exceed any applications or use cases that are currently subject to digital computation. And I think that's a trap we've fallen into as an industry, is that we're trying to do things that we've seen happen at the digital level or through digital computation, and we're simply not seeing or asking the right questions to penetrate further into mystery. So finally, the emergence of stable fourfold structure, whether atoms or cells, is essentially suggesting that these emergences have quantum dynamics implicit in them. And therefore, they themselves can be used to create this new genre of devices, and they will be fundamentally more stable and scalable since they are already stable at room temperature. Thank you.